Now this is back to chemistry 101. You put carbon dioxide in water, it just is going to react with water to form carbonic acid. If you've ever opened up a bottle of soda water and just before you take a drink you feel that little bit of sourness on your lip, that's the carbon dioxide, that's carbonic acid. It tastes a little bit sour. And this is just this simple reaction. CO2 dissolved in water, reacts with water to form this species called carbonic acid, which very quickly goes through these other reactions to produce bicarbonate, carbonate ion, hydrogen ions. These are the things that drive down pH. And finally, this one, which gets to why I think hydrogen ion is not the most useful. Carbon dioxide can react directly with carbonate ion to form bicarbonates. So essentially what happens here is if you put more of this in the water, you consume this. This goes up, this goes down, and it all sort of shunts over here into bicarbonate. And so it's maybe, and what I'm going to show you next, I think is going to show that maybe this, consumption of this species is maybe more important than the production of this. Okay? Or at least that's the one we should be paying attention to. The next thing that we know, again from thermodynamic principles, is that if you change the carbonate content in seawater, it changes how soluble carbonate minerals in contact with that water are. Right? So if you take dissolved calcium and dissolved carbonate, react it to form calcium carbonate, mineral phase. There are a number of different forms of calcium carbonate. I'll talk about that very briefly. This is a solid phase, okay? And it turns out, well, it doesn't turn out, but the way it works is that you can think about whether or not this mineral wants to precipitate or dissolve by the ratio of the concentration, product of the concentrations of these two divided by another thermodynamic constant. Okay, so this just tells you how inherently soluble this material is. Concentrations of these things tell you whether or not it wants to precipitate or dissolve in the water that it's sitting in. Okay? And this term, which is defined as this ratio, tells you that if it's greater than 1, precipitation can happen. And if it's less than 1, dissolution can happen. Okay? And there's lots and lots of things in the ocean that rely on calcium carbonate shells. These are coccolithophorids, and these and organisms like foraminifera are the basis for the white cliffs of Dover. Corals, obviously, are made out of calcium carbonate. They're a form that's actually a little more soluble than the coccolithophorid calcium carbonate. This is a material called aragonite, which has just got a different crystal structure. And it just thermodynamically likes to dissolve a little bit more than the calcite. Okay, how bad is it? Well, we know, again, because we know how much the carbon dioxide content in water has changed over the Industrial Revolution, we know that the pH has decreased by about 1/10 of a unit. Since this is a log scale, that's a 30% increase in acidity. And in a double CO2 world, which, you know, that's the conservative projection for the year 2100 in the IPCC scenarios, the change will be 0.3 pH units and a doubling of the acidity. Same time, the carbonate ion concentration has fallen by about 20% since the onset of the anthropogenic CO2 increase, and it's going to fall by about 60% in the double CO2 world. Now, in an ocean that's about pH 8, and is changing pH by about 0.1 or 0.2, it's unclear that there is any direct effect of the hydrogen ion content on organisms. There has been no experimental data or even theoretical suggestion that hydrogen ion itself is causing trouble or changes in organisms' behavior. Carbonate ion changes is a lot more obvious, at least to a chemist like me. Now, I'm talking to a lot of folks that probably understand organisms far better than I do. But this is just a nice, easy one. The carbonate ion goes down, carbonate minerals dissolve. That's simple enough for a chemist to understand. Now, this is some data that may have been the only good thing to ever come out of Biosphere. You guys remember Biosphere? remember the Pauly Shore movie, Biodome? I think the actual Biosphere might have been operated a little less ethically than the one we do. Now, what you may remember is that they built this big dome down in the Arizona desert, and there was going to be this utopian society, and there was a cult behind it that was going to show, I don't know, some sort of hypothesis coexistence, and they sent people in there to, you know, to live in this dome with a completely enclosed system that was going to be totally recycled, and of course they chose people that looked the best in spandex and and it turned out to really be a terrible experiment. And aside from the publicity-seeking aspect of it, one of the things they did is they built an ocean that had a coral reef in it, and somehow they messed up the chemistry inside that dome. And again, you know, some of you may not be old enough to remember this, but after a while, all those guys in spandex were starting to have trouble breathing because the oxygen levels just plummeted in there. And it was because I think they had too much humus in the soil and it was decomposing. And every day there would be a massive change in the carbon dioxide content in that atmosphere, in that artificial atmosphere, and the oxygen composition. And it was downward trending to the point that people were getting a little silly. And so they started pumping in clean air. And so they couldn't maintain their perfect system for very long. As a result of that, they were changing unintentionally the carbon dioxide concentrations in their ocean where they had a coral reef. And one of the guys that I worked with back at Lamont, at Columbia, was down there working on that reef, and they were really worried about it. And it turned out that if you look at the carbonate ion concentration in this water, where these corals were trying to grow, as a result of the changing CO2 levels, and measured the growth rates of those reefs at the same time, what you saw is this negative trend. The lower the carbonate ion concentration rate got, the slower the reefs grew. And you get down about to here, right about here is where the solubility threshold is for this mineral. And this line, you know, you can argue about the statistics, but it suggests that the coral reefs not only should dissolve down here, but they also just don't grow as fast when things aren't ideal, okay? So that got people pretty excited. And then folks did some modeling of the open ocean, and they calculated what the aragonite saturation threshold for this omega that I defined a couple of slides ago, what it was going to look like in the ocean in the year 2100 for a double CO2 atmosphere. And what they found out is that even in the places that were the best suited for coral growth, by the year 2100, they were getting down into these levels that the coral biologists considered marginal. Okay? And if you look at, for example, Hawaii looks like it just wasn't going to have any corals anymore. Okay. Now this is a model projection, but it, you know, was based on the best science that they could base a model on. Okay, a little closer to home. I mean, you know, there's no corals here, so who cares, right? People started doing experiments where they looked at the carbonate concentration dependence of the growth rates of a mussel species and an oyster species, commercially reported species, and what you see, again, is that as the carbonate ion concentration goes down, these calcification rates, these shell growth rates go down. And at the double CO2 atmosphere, the mussels calcify about 25% less than in the current atmosphere, and the oysters calcify about 10% less. Now, unfortunately, the oyster problem may be a little worse than this. Adult oysters, which is what these experiments were done with, grow their shell out of calcite, which is the less soluble, more stable form of the calcium carbonate mineral. The larvae, the planktonic larvae, before they settle, they form a shell when they're actually in the planktonic phase before they stick onto a rock or a wire or an oyster farm. And they don't form it out of calcite, they form it out of an amorphous form of aragonite, which is extremely soluble. And the oyster hatcheries in the Pacific Northwest are just about going under. Right? The guys at Whiskey Creek up in Netarts Bay pretty much say they've got one more year of this before they're done. And they've been having trouble with settlement where these planktonic organisms appear to be physiologically fine. They grow, they metabolize, but they never grow their shell. Okay? And they can do that for about 2 weeks and then the whole culture dies. Okay? And so far it looks like these failures have been associated with more, I'm going to say mostly natural events that have led to elevated corrosivity to the shells that these organisms are trying to form. Okay?